In this video, we'll begin exploring some common data preprocessing methods. These are generally grouped into four main categories: data cleaning, data transformation, data discretization, and feature engineering. In practice, we might need to apply all of these methods in some cases, while in others, just a few simple techniques will do. Additionally, for specific tasks, some of these techniques might overlap across the categories. First, let's look at the main tasks and methods involved in data cleaning. The most common issues that data cleaning focuses on include handling missing values, reducing noise, and correcting inconsistencies. There are some straightforward methods to address these problems, like deleting problematic data points. Since these are pretty simple, we won't spend too much time going over them. However, for more advanced concepts, like data imputation, we'll take a deeper dive and provide a detailed explanation. The first technique we'll focus on is data imputation, which involves using a reasonable estimate to fill in missing values. Essentially, data imputation is about finding logical and accurate ways to estimate missing data points. By filling in these gaps, we can maintain the dataset's integrity, keeping it as complete as possible for effective analysis and modeling. First, think about this. Why not just delete the data points that have missing values? Compared to simply deleting data points with missing values, data imputation helps preserve the integrity of the dataset as much as possible. Removing data points reduces the overall size of the dataset, and if this reduction isn't evenly distributed, like if certain categories lose more data points than others, it can lead to the model overfitting specific types of data. This could result in a biased model, so we should avoid deleting data points without careful consideration. That said, the decision also depends on the dataset itself. If each category already has a large number of data points, removing a few problematic ones might be a more efficient and practical option. Striking the right balance depends on the task and the specific characteristics of the dataset. Keeping the dataset intact allows the model to consider all the data points during training. This makes it easier for the model to pick up on the underlying patterns in the data, which ultimately boosts its performance. One of the simplest and most common ways to handle missing values is to replace them with the mean, median, or mode of similar data points. For numerical data like 1, 2, and 3, if the distribution is normal, the mean is a reasonable choice for imputation. For example, in a dataset with 5 data points where one value is missing, we can calculate the mean of the remaining 4 data points and use that value to fill in the missing entry. When numerical data includes obvious outliers, like 1, 2, and 1 million, it's better to use the median instead of the mean. In such cases, the dataset no longer follows a normal distribution, and the median is less influenced by extreme values, making it a more reliable option for imputation. The last scenario is when the data is categorical instead of numerical. For instance, in this dataset, we have 6 data points representing colors, with 1 value missing. In such cases, the most common method is to replace the missing value with the mode, which is the most frequently occurring category. This ensures the imputed value matches the overall distribution of the categories in the dataset. We can count how often each color appears in the dataset. For instance, red shows up 3 times, green once, and blue once. Obviously, red is the most frequent color, meaning the mode of this dataset is red. So, the missing value is most likely red. Therefore, we replace the missing value with red. Replacing missing values with the mean, median, or mode is one of the simplest and most widely used methods. Even though it's straightforward, this approach is often highly effective. However, for more complex problems, like when a dataset has multiple features and each data point is a tuple with several elements, the mean of a single feature might not fully capture the relationships between data points, since each data point contains multiple dimensions. In these cases, calculating something like the mean can be difficult or even impractical. That's why we need to turn to more advanced methods to handle missing values effectively in such scenarios. Here, we'll focus on discussing k-nearest neighbors, or KNN for short. The main idea of KNN is to find the k-nearest neighbors to the missing value and use the mean or mode of those neighbors to fill in the gap. In this context, neighbors don't just mean data points that are physically next to each other in the dataset. Instead, they refer to the data points that are the most similar to the missing value in terms of logical relationships. One of the biggest challenges in KNN is figuring out how to identify these neighbors. This requires defining the distance or similarity between data points based on their features. Let's start with a simple example. In this case, we have a sorted dataset where each data point has only one feature. Based on this, the neighbors of the missing value are 5 and 7. If we set k to 2, meaning we only look at the two closest neighbors 5 and 7, we can calculate the mean as 6. So, we use 6 to replace the missing value. Now, let's look at a more complex situation, a dataset with multiple features rather than just a single value. In this dataset, each row is a data point, and there are 3 columns representing 3 features: bill amount, wait time, and tip. One of the data points is missing a value for the wait time feature. This makes the problem more challenging because we now need to consider all the features to accurately identify the neighbors and estimate the missing value. In this case, if we want to use KNN, the most straightforward approach would be to focus on the wait time column, identify the neighbors of the missing value, and calculate the average. If we set k to 2, the two closest neighbors to the missing value are 24 and 53. Calculating their mean gives us 38.5, so we use 38.5 to fill in the missing wait time value. However, did you notice any potential issues with this approach? The main problem is that it only considers the wait time feature and completely ignores the other features, like bill amount and tip, in a dataset with multiple features. Focusing only on the column with the missing value can result in inaccurate estimates, as it fails to account for the relationships between different features. If we take a closer look at the dataset, we'll see that the data in the wait time feature seems disorganized and random. We can't directly assume that the missing value is related to 24 and 53 because using them to calculate the mean would be overly arbitrary. This points to a key issue. Relying only on the values in the wait time column, without considering the broader structure and relationships within the dataset, can result in inaccurate and unjustified imputations. To fix this, we need a more comprehensive approach that uses all available features to identify logical neighbors for the missing value. Furthermore, if the dataset has the wait time feature sorted, as shown in the figure, can we directly apply KNN to solve this problem? The answer is no, because we don't know the exact position of the missing value. If we simply place the missing value at the end and assume that 50 and 53 are its two closest neighbors, this approach would be arbitrary and unreliable. It overlooks the overall context and relationships in the dataset, which can lead to inaccurate estimations. Moreover, sorting by wait time alone ignores the relationships between features. KNN is based on finding logical neighbors by considering the overall similarity between data points, not just their closeness in a single feature. You might think, since the missing value affects the sorting of wait time, why not sort the dataset by bill amount instead? This could help us estimate the position of the data point with the missing value to some extent. This idea seems reasonable, as a larger bill amount might suggest the customer ordered more items, which could lead to longer wait times. Sorting by bill amount might provide a logical way to approximate where the missing value fits within the dataset. Using this approach, we can apply KNN to estimate the missing value. By sorting the dataset based on bill amount, we identify the two nearest neighbors of the missing value in terms of wait time as 9 and 53. The mean of these two values is 31. So, we replace the missing value with 31 based on this calculation. However, while this approach might seem more reasonable, it still relies on a strong assumption that bill amount determines wait time. This assumption doesn't always hold true. While a larger bill amount might sometimes correlate with longer wait times, many other factors could influence wait time, such as the restaurant's efficiency, the time of day, or the complexity of the dishes ordered. Relying solely on this assumption, without validating the relationship between bill amount and wait time could still result in inaccurate imputations. If we look at the first data point, the customer only spent $14.75 on food but had to wait 50 minutes. This clearly shows that bill amount doesn't always determine wait time. Other factors, like kitchen delays, the type of food ordered, or peak dining hours, could have caused the longer wait time. On the other hand, another customer spent $65.12 on food but only waited 9 minutes. This clearly contradicts the assumption that bill amount determines wait time. If we rely on this assumption, the resulting model will likely produce inaccurate predictions. This highlights the risk of making strong, unvalidated assumptions and emphasizes the importance of considering multiple factors and their relationships when addressing missing values. Similarly, if we sort the data by tip to determine the k-nearest neighbors for the missing value, it would still be an arbitrary choice. While it might sound reasonable, such as assuming that longer wait times lead to smaller tips, this approach is still based on an invalidated assumption. However, if the dataset only has two features, wait time and tip, using this assumption to find the nearest neighbors becomes more justifiable. In this case, we are making the best use of all the available data, and while the assumption isn't perfect, it seems reasonable within this limited context. Even so, this approach should be used cautiously, keeping its limitations in mind. However, in this dataset, we have three features. Even after excluding the column with the missing value, we still have two available features. We should make full use of both features to determine the nearest neighbors for the missing value. By taking into account both bill amount and tip, we can calculate the overall similarity between data points in a more comprehensive way, rather than relying on just one feature. This approach makes it more likely to identify meaningful and accurate neighbors for imputing the missing value. When a data point has multiple features, Euclidean distance can be used to measure the distance between them. In a two-dimensional feature space, the Euclidean distance between two points is calculated using the Pythagorean theorem. This formula gives the straight-line distance between the 2 points in the feature space, making it a straightforward and effective way to quantify their similarity. Similarly, Euclidean distance can be easily extended to higher dimensional spaces. To do this, you simply add up the square differences for all the features and then take the square root of the total. This method works for any number of features, making it a versatile and powerful tool for measuring distances between data points in higher dimensional spaces. Now, let's revisit the original example. From our earlier analysis, we know that we can't simply assume the blue and green data points are the two nearest neighbors of the red data point. Instead, we need to calculate the Euclidean distance from each data point to the red data point. Once we have these distances, we sort them in ascending order. The two smallest distances will give us the two nearest neighbors of the red data point. This ensures we are identifying the most logically similar neighbors by considering all the available features. Specifically, we can assign bill amount as the x value and tip as the y value. For the data point with the missing value, its x value is 77.87 and its y value is 0. Similarly, to calculate the distance between the first data point and the data point with the missing value, we first extract the x value and y value of the first data point. Then, using the Euclidean distance formula, we compute the distance between the first data point and the target data point. We need to calculate the distance from each data point to the target red data point, one at a time. After computing all the distances, we compare their magnitudes. Based on these comparisons, we identify the two nearest neighbors of the red data point, which are the green data point and the blue data point. These points have the smallest Euclidean distances to the target. All we need to do is calculate the average wait time of the two nearest neighbors and use that average to replace the missing value. That's the entire process of k-n. There are two key points to consider. The first is the choice of k. When k is small, the randomness of the imputed value increases because fewer data points are being considered. When k is large, more data points are included, which can reduce randomness but might also introduce unnecessary or irrelevant influences. In practice, it's best to manually review the dataset, examine its distribution, and then decide on a reasonable value for k. The second important factor is determining the nearest neighbors. If there's only one feature, sorting or comparisons can be used to find the closest neighbors. But when there are two or more features, it's necessary to calculate the Euclidean distance between each data point and the target to accurately identify the closest neighbors. In practice, k-n calculations are often performed using predefined functions. However, Because KNN is such a critical technique and its logic extends beyond just data preprocessing, it's crucial to understand the underlying concepts. This foundational logic will be an important focus in future exams, so make sure to master it thoroughly. By the way, I'm not sure if this is your first time learning about Euclidean distance, but it's a widely used and important tool for measuring distances in fields like machine learning, data mining, and artificial intelligence. In this course, you'll be expected to manually calculate distances for simple datasets. That wraps up the basics of data cleaning and the section on data imputation. In the next video, we'll dive into how to reduce noise in a dataset.